Hello, and welcome to Lesson 5 of this Introduction to Probability of Wolfram U. The topic for this lesson is equally likely outcomes. Let's begin. You may have the intuition that the concepts learned so far can be practically applied, but we haven't really done so far. So, to apply probability, you need assumptions. Assumptions simplify the complexity of real situations, and thus it's easier to compute, and we can then analyze and predict different outcomes. So, in this lesson, we'll focus on assumptions. The first common assumption is equally likely outcomes. For a sample space S of size n, all outcomes are equally likely if all of the outcomes have equal probability. So, each outcome should have a probability that is equal, and so since the sample space is of size 1, you should have each of the outcomes being of a probability of 1 over n. More generally, if an event E is in the sample space S, then the probability of the event is the number of outcomes in the event. So you add up all the outcomes and divided by the number of outcomes in the sample space. Let's consider a few examples. If you flip a fair coin, it's either heads or tails. So that means heads is 1 over 2, since there's 2 outcomes. If you roll 2 fair 6-sided dice, what is the probability that you get of sum of 7? Okay, so the different ways to make a sum of 7, there's 6 different ways to do that. So 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, and 6 plus 1. And then the total number of arrangements is 6 times 6 for the 2 dice. So that would be 36. So 6 divided by 36, you end up with 1 over 6, and that's your probability. Okay, another question. When you draw 5 cards out of a regular 52 card deck, what's the probability that you get a 4 of a kind? So there's 13 types of cards in a regular deck, from ace to king. And so that would make 13 different 4 of a kinds. And then the last card, you can choose any card for the remaining 48 cards. So that makes 13 times 48 for the number of arrangements of our event. Then the sample space is choosing any 5 cards out of 52 cards. And that would mean the binomial 52, 5, because the cards are unordered. So the probability is 13 times 48 divided by the number of the binomial 52, 5. Assuming equally likely outcomes, probabilities is not really how it's expressed usually. Usually we talk about odds. Odds can be written as a ratio A on B, A to B, A colon B, or A against B. You get the impression that this can be very dependent on the context. My personal favorite is A against B, but you can choose your own. Odds are by definition the number of outcomes of the event against its complement. Let's say you run for club president, but the odds are 1 against 5, so against you. Well, if you add 1 plus 5, you get 6, and so your probability of winning is actually 1 over 6. If you cheat in the game and your win ratio is 7 to 3, how likely are you to win? Well, you win 7 times and you lose 3 times, so the total is 10, and so your probability is 7 over 10, or 70%. As an example, consider 3 groups of marbles: 11 yellow marbles, 9 red marbles, and 8 green marbles, all in the same bag. What are the odds that each color is drawn? Well, first you need to calculate it for the yellow marbles. So that would be 11 against the remaining, which would be 9 plus 8. That is the red and the green marbles. And then you can repeat the process for all the other colors. Here we use a table function to make it a bit more intuitive. While the equally likely outcomes assumption is often intuitive, it sometimes yields surprising results. So let's look at this interesting example. Imagine you have a group of n people in a room. What's the smallest n such that the probability of 2 people sharing the same birthday is greater than 1/2? So first you need your sample space. So that would be the number of possible birthday arrangements. And we can easily calculate that because anyone can be born in any of the 365 days. So 365 power n. Then you need the probability of the event, but it's difficult to calculate it directly. So we'll actually first calculate the complement. So the number of arrangements for n people that have no birthday that is shared is easily calculated as a partial factorial. So the first person would have 365 available days, and the next person 364, and so on n times. Now, we've taken the complement, so you need to take the complement of the complement to get the initial event. So we're just going to do that, 1 minus what we just calculated, and that should give us the probability that, indeed, two people now share the same birthday, at least. And so if you just check that and you compute in a table, you'll get that at n is equal to 23, the probability reaches slightly over 0.5, which is over 1/2. And so we have our answer. If you check in the interactive graph, you can see that the probability of two people sharing the same birthday rapidly increases to almost 100% at just 50 individual, which is, to say the very least, counterintuitive. Other assumptions include mutually exclusive events, which imply that the intersection of events is zero. That means that if one event is true, the other really cannot be true. For example, a square cannot be a circle at the same time. Assuming events are independent is another assumption for intersections. So independent events are events where probabilities are unchanged by other events. The probability of the intersecting event is equal to the product of each of the events. So in practice, anything that doesn't really seem correlated will be assumed to be independent. For example, during a storm, in the last minute, you hear thunder, you roll a 1 with a die, and your friend's black cat growls. Okay, well, all of those things seem unrelated, so let's try to calculate them. On average, you hear thunder every 5 minutes and the cat growls every 3 minutes. So then you have 1 over 5, 1 over 3, and then 1 over 6 for the dice. So you multiply all of these intersecting events, and that is actually the equivalent of multiplying all of the events together since they're independent, and you get your answer. You may have noticed that in the last example, we focused on minutes, but really, minutes are not discrete objects, but continuous. So, how did that work? Well, equally likely outcomes is an assumption that it is usually in the discrete context, but it has its continuous equivalent, and that's called the uniform probability assumption. Calculating probabilities with the uniform assumption becomes interval calculus. So you only need to calculate the probability of the event as the size of the interval of the event divided by the size of the interval of the sample space. The uniform distribution will be explained further on in lesson 16, so you'll get to know a bit more about that eventually. So, what should you remember about this lesson? First, the applications of probabilities use assumptions to simplify the complexity of real situations. That's crucial because otherwise we can't really evaluate any probabilities. Then, all the common assumptions. So you have equally likely outcomes, where all outcomes have the same probability. Then, independent events, where the probability of intersecting events is equal to their product. And finally, uniform probability, where all intervals of the same size have the same probability. But it may not be sufficient to just assume everything. What if events are dependent? What if you need that complexity and assuming is not sufficient? Well, the next lesson addresses this by delving into conditional probabilities.